Thank you for the introduction, and thanks to the organizer for arranging such a nice conference and also giving me the opportunity to present our recent works on I am not sure if this is working. Properly. Yeah, thank you. So our recent work is on spin orbitronics with a comparatively newer material, I would say. That's the potassium tantalate two-dimensional electron gas. So thanks to Laura that I don't need to introduce a lot this system, because like almost 20 years back, the oxide two-dimensional gas was first discovered in the interface between two insulating perovskite materials, that's lanthanum aluminate and strontium titanate, although they both were insulator, but due to the charge reconstruction in the lanthanum aluminate, there was a two-dimensional electron gas at the interface of these two materials. Later it was confirmed that this electron gas is 2D in nature, and also this shows many exciting properties like very high electron mobility at low temperature, high spin orbit coupling, low temperature superconductivity, very nice gate tunability, and many more. And because the title suggests that I'm going to talk about spin orbitronics, so of course this involves, like, we would like to do some spin to charge interconversion, and for this I need spin orbit coupling, and in this case this is controlled by the Rashba effect, but again, because Laura already explained everything, so I will skip this part. That we already know that if there is a Rashba effect present in the system, then we end up such kind of spin degeneracy lifted Fermi contours with opposite chirality, and there the spin and momentum are always locked to each other, and basically this Rashba effect is the one which enables the possibility to achieve the spin and charge interconversion in the system. And in case of, let's say, direct Edelstein effect, where we pass a charge current in such system, then the Fermi contours shift and there is a spin accumulation, and as they are not equal, so of course we have some spin density. So this is how we can have a charge to spin. This is the direct Edelstein effect, and we have the reciprocal effect of this, which is the inverse Edelstein effect, where passing a pure spin current, let's say by spin pumping, the Fermi contours will shift in opposite direction, and from this delta K we can have a generation of charge current, which is the spin to charge. So here one thing I would like to mention is the figure of merit lambda is the ratio between the charge current and spin current, and this depends on mainly on two factors. The first one is the Rashba coefficient of the system, and also the spin the momentum relaxation time. So it depends on both these factors. So, and then very quickly I will remind you just some like numbers related to the very conventional STO2 decks, which some of this you already saw in Laura's talk, that it has been also, like, it has been found like many years back that there is a strong gate dependence of the amplitude and as well as the sign of the Rashba coefficient in case of the STO2 decks. And the, like, so far the maximum alpha was found for STO2 decks was 50 milli-electron volt angstrom depending on the gate voltage. And in such kind of system, when the spin to charge conversion was done to find the conversion efficiency, so as the alpha varies a lot with the gate voltage, so of course the lambda also varied a lot with the gate voltage with the amplitude and sign. And the maximum for aluminium STO was found around 25 nanometer. So keeping these two things in mind, let's move to the main topic of discussion today, that's the potassium tantalate. So, so potassium tantalate in bulk has many similar properties like strontium titanate, like they both are quantum paraelectric, and it's possible to have like upon minute n-type doping, it's possible to make the bulk KTO also metallic, and also it shows quite high mobility. Now, why we chose KTO over STO, like the motivation of choosing this material is because the presence of this tantalum, because we know tantalum is heavier than titanium, so we think that the spin orbit coupling in KTO should be much larger than STO. This is why we started working on this. And then it's also possible to have 2D electron gas in KTO. We can do similar deposition of other insulating perovskites like lanthanum aluminate or LTO, LBO, many other. And we think that the Rashba spin orbit coupling in KTO 2DEX should be much larger than STO because of the larger spin orbit coupling due to tantalum. And already there were, like before we started working on this, there were few reports where people already started working, and it was reported that the alpha value found in case of potassium tantalate was like 70 milli electron volt angstrom. So already we see some improvement in compared to the STO case. And now in our case, what we did for our sample is very simple. So Laura also mentioned about this, that by Rodel et al. It was shown that without even depositing any perovskite materials, it's also possible to achieve the 2D electron gas. And in this way, basically, you don't go to any high temperature growth, or you do not need to use PLD. It's just by depositing metal on top of STO or KTO. And when you deposit metal, basically the metal becomes oxidized by taking oxygen from the substrate. And thus you have oxygen vacancies at the interface between this metal oxide and the substrate. In our case, it's KTO. And due to these oxygen vacancies at the interface, you end up of having the 2D electron gas. So this is what we did, like we deposited aluminium by DC sputtering at room temperature on top of potassium tantalate, and we tried to study the valence states of the tantalum to know if there is any oxygen vacancies creating in the system or not by X-ray photoelectron spectroscopy. So when we, like this is the bare potassium tantalate substrate, and here we can see that only the tantalum 5+ state is present. This means that there is no oxygen vacancies present in the system, it's purely insulating. And then when we deposit, let's say just 4 angstrom of aluminium, we can already see the evolution of peak corresponding to tantalum 4+, telling us that oxygen vacancies are created in the system. And as we increase the thickness of aluminium, we can see that the intensity of the peaks corresponding to tantalum 4+ increases, and as well as there is a new peak now corresponding to tantalum 2+, telling that like we have oxygen vacancies at the interface, and in turn which is giving the 2-dimensional electron gas in the system. And we did the transport property measurements also, where we can see like by varying the thickness of aluminium for all of the sample, we have very nice Arvar-Sesti measurements, nice metallic curve. And from the Hall measurements, we calculated the carrier densities as well as the mobility of the samples. And the mobility of these samples were of similar order of magnitude what we earlier got in case of, let's say, aluminium STO samples. And now in this system, because I said that this is really new, not much explored, so we wanted to understand the band structure of this system. So what we did is we did angle resolved photoelectron spectroscopy, that's ARPES, to visualize the band structure of the potassium tantalate. And for this, we grew 1 or 2 angstrom of aluminium by MB on KTO. And here we used MB because this MB is in situ connected with the ARPES chamber. So we grew the sample there and immediately measured. And this is the band structure observed for KTO. And to understand this band structure more, we collaborated with the group of Ingrid Martig in Halle, who, like their group, they perform the tight binding fits for this so that we can really understand this. So the tight binding fits like matches very well with the band structure observed, and here we can see that like there are few band pairs which are contributing to the transport of the electrons. So here the pink band, like there are always like they are band pairs. So the pink and the green, they are with dxy characteristics. So they are the light bands, and there are heavy bands with dxz, like mixed orbital characteristics. These are these orange bands, and they are basically the most Rashba splitted bands. And we can see from the zoomed version of this that for the first time for, let's say, any oxide perovskite material, it was possible to resolve the Rashba splitting using the RPS measurement. So clearly we can see like there are splitting between these two bands, which corresponds to the Rashba splitting according to the tight binding fits. And from this tight binding fit, they calculated, basically Annika and Borge, they did the tight binding fits for this, and they got the alpha value of 320 milli electron volt angstrom, which is really one order higher than the STO2 dex. So this is really huge what we observed, and of course we wanted to like experimentally measure this. So for this we took advantage of the direct Edelstein effect, that is the charge to spin conversion, and basically in our sample we passed a charge current, and due to the direct Edelstein effect the spin density is generated transverse to this direction. And now if this sample is rotated in plane with respect to the magnetic field, then the angular dependence of the resistivity looks like this, where it is dominated by these two terms. The first one is known as the bilinear magnetoresistance, which varies as the sine theta, and the second term corresponds to the quadratic magnetoresistance, which varies as the cos theta. And if we try to look at the coefficient of these two terms, the first one varies linearly with the current density as well as the magnetic field, and for the QMR the coefficient varies quadratically with the magnetic field. So we did measurement in our sample, and we can see like BMR really varies like sine theta, and QMR varies like cos 2 theta as expected, and also the coefficient of BMR varies linearly with both the current density and the magnetic field, and for QMR it varies quadratically with the magnetic field. Now here if you see that the coefficient of BMR consists of the Rashba parameter, the Rashba coefficient. So basically if we try to take the ratio between BMR and QMR, this tau square will cancel out, and from other parameters it is possible to estimate the value of alpha experimentally using this technique. And this is what we did, and we found the estimated alpha between 70 to 280 milli electron volt angstrom, which matches quite well with the theoretical like tight binding fits what we observed in case of our RPS measurements. So now we see that we have really nice, like very high alpha values in our sample. So we wanted to study the spin to charge conversion of this, and for this we did the inverse Edelstein effect measurement, and because we need to do spin pumping to inject the spin current, so we need a ferromagnetic layer. So on top of aluminium oxide, now we have a permalloy layer on top of this, and this spin pumping measurement was actually carried out in group of LoRa in SpinTech Grenoble, and what we see is like quite nice spin to charge conversion is happening. We can see exactly at the ferromagnetic resonance, we see very nice symmetric signal corresponding to inverse Edelstein effect. However, when we calculate the lambda, it came out close to 3 to 4 nanometer, which is like similar order of magnitude with STO. So I told you that we are gaining almost like 5 to 6 times with alpha than STO, but then we finally end up with this similar order. So here another factor is varying, that's the tau, And the tau basically depends on the mobility of the samples and the effective mass of the electrons. And in case of STO, the effective mass of electrons are like 5 to 6 times larger than the effective mass of electrons in KTO. So basically, although we gained like 6 times in alpha, but finally we lost similar amplitude in case of the tau. Now we cannot, of course, improve the effective mass because this is the property of the KTO. But what we can do is we can improve the mobility of samples. Like we need to grow some samples with much higher mobility so that we can increase tau. And if we can increase tau, finally with this very high alpha, we think it will be really promising to have very high spin to charge conversion in this material. Now let's try to understand, because for the moment what we see is just the spin-Edelstein effect. So we believe that there will be some orbital contribution in this system too. So we wanted to understand more like what happens if we want to see the spin-Edelstein effect as well as the orbital Edelstein effect. So for this we did some theoretical calculations. Basically it's again Annika and Borge with in the group of Ingrid Marti who did these theoretical calculations. So I came back to the band structure which I already presented to you earlier, and now I will first show you the spin and orbital textures calculated for each band pairs close to the band edges. So let's start from taking iso energy line here close to the pink band edge to see how it happens. And also for these images I would like to show define some nomenclature. So from now on, for all the images I will show, the top quadrant will carry the information about spin, the bottom quadrant will carry the information about orbital, the right quadrant shows information about the inner band, and the left one shows the information about the outer band. So this nomenclature I will follow for everything from now on. And let's say for this specific energy we can probe the band pair, and here this shows like usual Rajba-like spin and orbital textures, which we can see that spin and momentum are locked to each other, very nice circular band structure. And if we increase the energy from here to here so that we can start seeing the green band pair, then still we are in the Rajba-like texture. And when we calculated the splitting between the two pink band pair and between the green band pair, this is more or less similar, giving the alpha close to 10 milli-electron volt angstrom. However, we are of course more interested about the orange band pair because this shows the largest Rajba splitting. So when we went to higher energy close to the band edge of the orange band pair, we can see that due to the orbital mixing between the dxz and dyz, basically its orbital like the orbital characteristics are mixed in case of the orange band pair. So finally we are like, if you see the length of the spin, they are much reduced in compared to the pink and the green band. So this tells us that probably, although the splitting is quite high, but probably when we will calculate the spin and Edelstein effect, finally we will not get very high efficiency, because the spin texture for the dxz, like the sign of the spins for dxz and dyz, they are opposite to each other. So finally they are cancelling out each other, and this is why we are ending up with a very small length of the spins. And also here we can see for the pink and the green band pair, they are deviating from the pure Rajba model, because now there is orbital mixture between dxy, dxz and dyz. So because of this orbital mixing, now no longer they are following the pure Rajba model. So according to the pure Rajba model, normally the spin should rotate 2 pi in a circle. But in this case, for the orange band, we see it's a 6 pi rotation in the circle, which is completely deviating from the Rashba model. And as we increase the energy from here to close to the cyan band, although the cyan band shows Rashba-like spin and orbital texture, but as I said, like here we are seeing more complicated stuff, because for the green band, it's expected from the theoretical calculation that they will, like there is a crossing between the two pairs of the green band, and also the orbital characteristics get mixed. So no longer they are circular, they are completely deviating from the Rashba model, and also giving very, very complex spin and orbital textures of like 10 pi rotation over the full circle. So it's not at all matching with the Rashba model. And then we calculated the band resolved spin and orbital Edelstein effects also. So this one, the top part, this carries the information about the spin Edelstein effect. So we move in the we move the Fermi level in the energy. This is here plotted, and we can calculate, like as more and more bands get involved, we can see how the spin Edelstein effect varies. So basically, the sign of the Edelstein effect can be positive or negative depending on the chirality of the bands. And here one special thing we observed, that's a kink, a sudden kink in the spin Edelstein effect in case of the green band pair, and this is because, as I said, close to this energy there is a band crossing between two pairs of the green band. So this is why we see a kink here, which is also like evident from the total spin Edelstein effect. And in case of the orbital Edelstein effect also, we see similar trend. But what is interesting is that the orbital Edelstein effect is almost 10 times larger than the spin Edelstein effect. So experimentally, we were always just probing the spin Edelstein effect, but if somehow we can probe the orbital Edelstein effect also in the samples, we can see that this is like more in amplitude than the spin Edelstein effect. So this is why when we calculate the total Edelstein effect present in the system, then of course the orbital Edelstein effect dominates the total Edelstein effect. And also anyway the spin Edelstein effect, although it was not okay. Another thing is for the orange band pair, although they are the largely Rashba splitted, but finally they did not give the highest spin Edelstein effect or the orbital. Finally, it's coming from the pink band pair, this one, because with the orange one, it's mixed orbital characteristics. So we also saw from the spin texture that the length of the spin textures were really small. So we expected that finally, like they are compensating the dxz, dyz, they are compensating each other because they are opposite in sign. So finally, we are not gaining from the very high, high Rashba splitted bands. And if we compare between the KTO and STO, then the maximum spin Edelstein effect of KTO is still like factor of 2 larger than STO, and for orbital Edelstein effect, it's like factor of 4 larger. So from here we learned few things. I don't know how much time I have. Okay, perfect. So we learned few stuff like there are mainly 3 compensation effects. The first one is the Edelstein effect from the dxz yz band. They are opposite in sign. So this is why for the orange one we have less Edelstein effect. Then also the sign between the dxy band and the dxz yz. So this is also opposite in nature. So finally, this is why the total Edelstein effect is also getting reduced. And then the spin Edelstein effect and the orbital Edelstein effect, they are also opposite in sign. So this is why the total Edelstein effect is also not very, very large as we were expecting initially. And to resolve this kind of issues, let's say for the first issue, what we can do is we can introduce some anisotropy in the system, because initially for the isotropic case, it was considered that it's exactly equally mixture of dxz yz band. But now we are considering an anisotropy case where it's not equally mixed, and here because of this anisotropy, we can see for the orange band pair a large increase in the spin-Edelstein effect. But finally, the total Edelstein effect is not just from the orange. It also has a contribution from other band, and this affects. So this is the same. So even introducing anisotropy, we could not really like improve a lot. And for the second and third, what we can do is maybe we can generate 2DEG in materials where the dxz yz band will lie below the dxy, so that we can have same sign of the dxy and dxz, which can increase in the spin-Edelstein effect. And also we can choose materials where the spin and orbital moments will be parallel to each other to gain in the total Edelstein effect. So with this, I would like to summarize my talk by telling you that probably I could show you that just by simple sputtering, it was possible to achieve the 2DEGs in potassium tantalate, and it shows really high spin Rashba spin orbit coupling. And the theory predicts that the orbital effect is like 10 times stronger than spin-Edelstein effect. So although we see strong compensation effect, but we also propose some possibilities to get rid of this, and as perspectives, probably we can grow higher mobility sample to have more spin to charge conversion. And also if we can utilize the orbital Edelstein effect along with the spin-Edelstein effect, this will be really nice. And recently, like last year, it has been seen that KTO 111 and 110 2DEGs, they are also superconducting with a superconducting TC 1 order higher in magnitude than the STO, and we started working on these, and we also saw superconductivity. So we believe, we saw yesterday in Martha's talk that it's exciting to like couple the superconductivity and also orbital Edelstein effect. So we believe this will also have some perspectives in future. And thanks to all my group members and all the collaborators who participated in this work, and thank you for your kind attention.